Good afternoon, everyone, or good morning to you on the West Coast. I can see that we've still got a few people that are joining in currently, so we will begin our webinar here momentarily. Thank you for your patience. Okay, welcome everybody to today's webinar. My name is Jill Browning, and I will be your moderator for today's webinar on CoStrip, a robust degasification technology. Before we get into today's presentation, I do have just a few housekeeping slides to go over. First of all, it should be obvious that hopefully you should be hearing me now, but if you do have any difficulties throughout today's webinar, I just wanted to mention that there are two different ways to connect to the audio. You can connect either using your computer audio or via your phone. So feel free to switch between the two if for some reason one of those has any difficulties. And also, due to the large number of attendees on today's webinar, we have muted everyone's phone lines, but no worries, we do still have an option to interact with today's panelists. And in terms of interacting with the presenter today, you can type your questions via the questions panel anytime throughout the webinar. And then at the end of today's presentation, we do have some time set aside to answer as many questions as time allows. So feel free to ask any questions that come to mind, and we will try to get through as many of those as possible. And if you haven't seen it already, today's presentation is one of several that we are conducting through a 3-week live series. You can check out the complete series at our website, www.veoliawatertech.com, and access the schedule there as well as register for those upcoming events. And in addition to the live webinar series that we are conducting, we have also made available our collection of on-demand webinars that we've conducted over the past few years. So you can also access those on-demand webinars at www.veoliawatertech.com. So feel free to take a look at all of those as well and register for those. Another housekeeping note, we are offering a PDF participation certificate that will be made available to you after the webinar. You should receive it within probably 24 hours. If for some reason you do not, feel free to reach out to us. And finally, something fun to do, but also really helps us, is your feedback. At the end of today's webinar, you'll receive a quick survey that is requesting your feedback. It should take only 20 to 30 seconds of your time. And for those of you who do complete the survey, you'll be entered into a drawing for a chance to win a $25 gift card from Amazon. So if you are the lucky recipient of that or the lucky winner, we will reach out to you after today's webinar. Okay, one more quick slide before I introduce our speaker today. Veolia Water Technologies. We are a leading company within water treatment. We do focus our efforts in 3 key main areas. Technologies, we offer advanced and robust water treatment technologies. We do have a large portfolio of over 350 proprietary technologies that we do offer to our clients. In addition to technologies, we're able to pair those technologies in terms of developing projects for our customers, and also put together multiple technologies to meet the required treatment specifications of the client. And then lastly, We have a thorough service offering that we can provide, whether it's during the projects or after. And now I'd like to introduce our speaker for today's presentation. Kim Fernandez is a process engineer at Veolia Water Technologies. Kim graduated with a BS in chemical engineering from Texas A&M University and has worked as a process engineer at a petrochemical plant for over 7 years before joining Veolia. And now I'd like to turn it over to Kim. Kim, are you with us today?
Yes, thanks, Jill. Hello, everyone. Hope you're all staying safe and healthy. Today, I'm going to be talking to you about Veolia's CoStrip technology. This is a degasification process that removes dissolved gases from water. I'll take you through where this technology can be applied, how it works, and the various factors that affect the performance. So first, let's take a look at what gases are present in water and why we need to remove them. Contaminated water usually contains various VOCs and acid gases. VOC stands for volatile organic compounds, and these can be toxic and corrosive and must be removed to reduce safety risks, environmental emissions, and improve equipment reliability. The VOCs that you see here are commonly known as BTEX, which stands for benzene, toluene, ethylbenzene, and xylene. These, even in small amounts, can be detrimental to plant personnel. To put that in perspective, benzene has an OSHA permittable limit of 1 ppm for an 8-hour period. Another gas that often needs to be removed from water is H2S, which is part of the acid gases group. H2S tends to be flammable, toxic, colorless, and is a safety hazard for plant personnel, and has a limit of 10 ppm for an 8-hour period. These are some of the gases that are present in water that need to be removed. Now let's take a look at how these gases can be removed. Conventionally, in order to strip dissolved gases such as CO2, H2S, and BTEX from liquids, usually a packed or a sieve tray tower is used, similar to what's shown here. A vacuum is pulled in the tower that allows the stripping of these gases, which is then sent to an off-gas stream for further processing. This works great for clean streams, but if the water is contaminated and contains suspended solids or oils or grease, like what you would find in produced water or flowback water, then the packing that you see at the bottom gets quickly coated with oils and solids, which then becomes an operational nightmare. Usually, there's pretreatment equipment that's put upstream to remove the oils and the solids and any scale formers prior to being sent to the degasification. Now, Veolia's CoStrip degasifier approaches the gas removal from a very different perspective. Veolia's CoStrip does not have packing or trays, and because of that, it's not susceptible to fouling and is able to handle high levels of oils and solids, along with high dissolved gases that come in the water without the need for any upstream pretreatment equipment. The CoStrip unit that you see on the top right corner here is a horizontal vessel where the water comes in through one end, goes through the vessel of 4 cells, and then comes out at the other end. This unit right here is our pilot unit, and it comes as a complete skid with the vessel, the effluent pump, an acid skid, all the instruments, valves, and also a PLC panel. The bottom picture that you see right here is one of the cells that are in operation. The blue arrows show the path that the water takes as it travels through each of the cells. The cells are separated by baffles. Each cell, as you see, is equipped with an inductor that uses the recycled effluent water and fresh gas to produce microbubbles. You can see the microbubbles as these white dots in the cell. These microbubbles act as sponges and are dispersed throughout each of the cells to allow for maximum contact with water. As water passes through each of the 4 cells, it provides a longer contact time with the microbubbles and the water, thus achieving a higher percentage of removal of the contaminants. Another thing you'll see in the picture is a laundry chamber that's also provided in each cell. It's there in case that you need to remove any oils or solids that have collected on top from time to time. The water in the cell tends to be very turbulent, so you don't usually see a whole lot of removal of oils and solids. As you saw in the previous slide, microbubbles are an integral part of the system. The microbubbles are usually about 50 to 150 microns and are introduced at the bottom of the vessel through the inductors. The size of the microbubbles play 2 important roles. One, it provides a greater surface area or a gas-liquid interface. And 2, the smaller the bubbles, the longer it takes for the bubbles to go from the bottom of the vessel to the top. These are important because both of these allow for a longer contact time for the mass transfer to take place. As these bubbles rise through the liquid, dissolved gases in water such as H2S, CO2, and BTEX diffuse into these bubbles. Once they reach the top of the water, the surface of the water, the microbubbles pop, releasing the absorbed gases into the headspace. The gas on top of the water is continuously swept, and fresh gas is introduced, thus providing a constant gas disequilibrium with the system. This is explained by Henry's law. Henry's law states that at constant temperature, the amount of a gas that dissolves in a liquid is directly proportional to the partial pressure of that gas in equilibrium with that liquid. We'll explain that using this equation. So let's take H2S, for example. The equation says that partial pressure of H2S in the gas phase is equal to the Henry's law constant for the gas, the temperature of the liquid, and the concentration of the dissolved H2S in liquid phase. Meaning, if you have one gas at a constant temperature, H2S dissolved in a liquid is directly proportional to the partial pressure of H2S in the gas phase. This is the principle behind the CoStrip technology. The CoStrip works by continuously driving a disequilibrium, thus forcing gases from the liquid phase into the gas phase. This is achieved by introducing fresh gas in each cell through reductors and then continuously sweeping the headspace to remove the contaminants. Again, if you look at the equation, you'll see that if you keep the K and the T constant, P over C remains a constant. That means for a given gas at a constant temperature, P over C is a constant. P over C is called the partition ratio. And this represents the distribution of the dissolved gas between the liquid phase and the gas phase. An important thing to note is that the partition ratio is independent of the concentration of gas in the bulk liquid. Meaning, regardless of the concentration of the dissolved gas that's coming in to the CoStrip, the P over C ratio, the partition ratio, remains a constant. This allows the CoStrip unit to work with liquids at very high concentrations of thousands of ppm or even at very low gas concentrations at ppb levels. It gives the CoStrip a wide flexibility to work with various concentrations. Now let's take a look at what are some of the factors that affect the performance of CoStrip unit. First is the stripping gas flow rate that's put into the unit. As you'd expect, the more gas you would add to the system, the higher the removal. Here you can see the first chart is for carbon dioxide removal. And if you put in 2 SCF per barrel, you get a 50% removal. And if you put in 4 SCF per barrel, you get a 60% carbon dioxide removal from the water. And you can see how it jumped from 50 to 75. Same thing for H2S removal at the same temperature. If you go from 2 to 4 SCF per barrel, you increase the removal rate from 30 to 50%. Now, one thing you'll see that both these charts look different because one's for carbon dioxide, one's for hydrogen sulfide. The difference, the reason why these are different is because both these gases have different Henry's coefficient, which then affects the partition ratio, which then affects the removal efficiency. Another factor that affects the removal efficiency is the temperature of the feed water that's coming in. Again, if you look at Henry's law equation, you'll see that as you increase the temperature, the P/C ratio will increase. Meaning, as the temperature increases, more contaminants are driven to the gas phase. If P/C changes, as you see here, at a lower temperature, you have more contaminants in the liquid and fewer in the bubble. And as the temperature increases and the P/C ratio increases, more gases are driven to the gas phase from the liquid. And you see all the way to the end, you have more in the gas phase than in the liquid phase. Now this is 2 charts, both for carbon dioxide removal. One is at 160 degrees and one's at 80 degrees. For example, let's take a look at 8 SCF per barrel. At 160 degrees, you see a 90% removal. But at 80 degrees, you only see about a 65% removal. It shows how temperature plays an important role in being able to remove as much contaminants from the solution. This, along with the gas stripping flow rate, can be used to figure out how you can achieve the required removal percent. For example, if you want to heat up your water and use less gas, then you can do that. Or if your water is cold and you're able to use more gas, you're able to get that using the removal efficiencies. Another factor that affects the removal of acid gases is the pH of the inlet water. This chart here shows how a change in pH can shift the concentrations of carbon dioxide, shown in the black dashes here, bicarbonates in pink, and the carbonates in the blue dashes. As you see in the red box, when the pH is higher than 6.5, the ionic forms such as carbonates and bicarbonates are preferred and less of CO2 is present in water. The problem with this is if CO2 is not present, it cannot be removed using CoStrip by absorbing into a gas bubble. So pH is usually lowered below 6.5 to make sure that the carbonates and bicarbonates are converted into carbonic acid, which is then diffused, which then dissociates into CO2 in water. There's a similar chart like this for H2S and converting to bisulfides and sulfides as well. Because the effect that pH has in acid gas removal, often the feed water that comes in has a high pH, and acid has to be dosed to reduce the pH to optimize the stripping efficiency. And usually you can use any type of acid like HCl or sulfuric acid, depends on what's available in the plant or what is good for the process. We've seen that CO2 removal is optimized between a pH of 6 and 6.5, and H2S is optimized around 5 to 5.5. It is important to note that the optimal pH ranges are application specific, and often factors need to be considered, such as feed water quality, temperature of the water coming in, the removal efficiency that's required, effluent water quality required, and of course the operational costs that go into it. Another advantage to reducing the pH and removing acid gases is the reduction of alkalinity in the water. The presence of carbonates and bicarbonates usually can cause scaling in downstream units. Keep in mind though, CoStrip does not remove all the alkalinity from water, it just removes the excess alkalinity. And the equation shown here, as acid is added, which is H+, the carbonate ions are converted to bicarbonates, which are then converted to carbonic acid, and in water it dissociates to CO2. Note that removal of each carbonate and bicarbonate ions can reduce the demand of chemicals that are required downstream in the downstream units, resulting in significant cost savings for the customer. Now we'll talk about the stripping gas. It's important to note that the type of stripping gas used does not have an impact on the performance since Henry's coefficient is dependent on the properties of the dissolved gas. So in the equation that we showed before, the property of the gas was the dissolved gas and not properties of the stripping gas. So you can use any type of gas as a stripping gas. Another thing to note is that the stripping gas must not contain any significant amount of contaminants that need to be removed. For example, if you're trying to remove H2S from water, don't use sour fuel gas because it contains H2S and it will affect the partial pressure of that gas. Instead, use sweet fuel gas or nitrogen or any other gas that does not have H2S. But also keep in mind not to use any gases that can cause a flammable atmosphere. Another thing to note is that the partition coefficient of each gas is independent of other gas species. Meaning if you're trying to remove more than one gas from the liquid, say CO2 and benzene, each of them have their own partition coefficient, and each of them have their removal efficiency, so they have to be treated separately. And as seen before, the higher the stripping gas flow rate, you get a higher removal efficiency. The off gas that is removed from the vessel can either be recycled or disposed. Some of the options are flaring using existing amine treatment, chemical scrubbing, thermal oxidation, biofilter systems, or self-ethane for H2S treatment. And now we'll talk about treatment of H2S in shale plays. CoStrip can be instrumental in removal of H2S from water that's contaminated, such as produced water and flowback water. These streams usually contain H2S from 5 to 600 ppm. We did a few pilot tests recently, and we were able to test the removal efficiency of H2S at various temperatures while keeping the pH and the stripping gas flow rate constant. We saw that at 70F, we got a 75% removal, and at 85, we estimate about 80% removal, and at 100F, about 85% removal. Another method that's commonly seen in produced water sites is to reduce H2S by dosing oxidants like chlorine dioxide or hydrogen peroxide. These oxidants usually help to remove iron, manganese, as well as reduce H2S and prevents scaling, souring, and bacterial buildup. Now, at low H2S, using oxidants is effective, but as H2S concentrations go up, the chemical costs become too prohibitive to use. For example, if you compare a 10,000 barrel per day system with 100 ppm H2S, using CoStrip can have a cost savings around 50 cents a barrel. Meaning, if you try to use oxidants and compare it to using CoStrip, you can have a lot of cost savings if you use CoStrip. Another advantage CoStrip has is that it can be integrated into shell-flow equipment or trains to minimize oxygen requirements, which can reduce the overall operational costs. If you have a lot of H2S coming in, you can first use CoStrip to knock down most of the gases, and then use oxidants to reduce it further to what is required. As discussed before, the flare or gas recycling is site-specific and can be done as the customer requires. In conclusion, CoStrip provides a unique fouling-resistant solution to remove dissolved gases, especially from contaminated water, such as produced water. It has also shown to be able to remove various dissolved gases and does not require a specific stripping gas or chemical to work, which means that a plant, if it already has a gas that's readily available to them, they can use that as a stripping gas. Also note that other than adjusting the pH, CoStrip does not require any other chemicals for it to work. Various pilot studies done show an average about 80% removal of targeted dissolved gases. This removal efficiency obviously can be adjusted by changing the parameters of increasing or decreasing temperature, gas flow rate, pH. But ultimately, the important thing is that the removal efficiency is driven by the need of the client and the required effluent water quality. If you see here, we published a white paper that was submitted to SPE, and this is the number on the screen. It has a lot more details on how it works and pilot test results in details. If CoStrip is integrated as part of a chemical softening drain, it can lower the chemical consumption and soot generation downstream, which can reduce the capital and operational costs. Similarly, when CoStrip is installed upstream of a membrane filtration system, it improves the life of the membranes by taking out any scalants that may be present in the liquid. With that, I'll turn it over to Jill for any questions. We also have Oscar Velastegui, our technology manager, online, and we can help answer any of the questions.
Great. Thank you, Kim, for that very informative presentation there. I just want to remind everybody, if you do have any questions, feel free to type those in on the questions panel over to the right. We do have some questions that came in, so I will get that started with Kim. Okay, Kim, the first question that we've got is, it's a two-part question here. what gas would be used to strip BTEX in an oil and gas application? And then similarly, what would be used for stripping acid gases?
So as we said earlier, we can use any gas that's available in the plant to use as stripping gas, both for BTEX and acid gases. Whatever is available can be used.
Okay, another question that we have is for oily waters, what is the maximum concentration of oil in the water?
Maybe Oscar can help with this one. We can get back to you guys.
Yeah,
on that one.
while we wait for Oscar on that, I've got a couple more that have just come in as well. Can this technology be used to reduce benzene to below 10 milligrams per liter? So downstream processes are exempt from BWON.
I'm not sure what BWOM is, but this CoStrip works by taking what's coming in and reducing the concentration. So, for example, I would need to know what the inlet inlet BTEX concentration is, and from there we can say, are we getting an 80% removal, or what is the percentage of removal? So if it falls within that, yeah, we can achieve below 10%, 10 ppm of benzene.
Okay, another one is, can influent water be used instead of effluent to inject gas bubbles?
Preferably, it's better to use effluent water, since when it doesn't have any of the contaminants in it. But also it depends on the application, depends on if there's already a pump present in for the feed, or if there's pressurized influent coming in. Preferably, because we have to put a effluent pump, it's more efficient to use the effluent as the recycle stream for the eductors.
And can we use air as stripping gas?
You can, but you have to remember air can cause a flammable atmosphere, so you have to take that into consideration. It just cannot contain any significant concentrations of what you're trying to remove in it as well.
Okay, and then also, what type of maintenance is required of the system?
I'm gonna give that to Oscar if he can answer that one.
Yeah, let me see. It appears that we've got Oscar muted. Give me 1 second if you'll bear with me here. Does not. I apologize. It appears that we cannot unmute him there. Oh, there we go. Okay, Oscar, are you there?
Yes, thank you very much. I was pressing unmute about 100 times and it didn't work. But anyway, back here. So for the first question, it says how much oil is, I guess, allowable here. We can say that we can probably take about 500 ppm of oil without any issues. We can probably take a little more, but we'll have to do some testing on it. Okay. Remind me about the next question.
The next question was in regards to reducing benzene to below 10 milligrams per liter. So downstream processes are exempt from BWON or BWON, perhaps?
Okay. If the question is that if we can achieve that low level, the answer will be yes.
Okay, great, thank you.
Mm-hmm.
And then also, what is the optimum gas bubble size?
Like we showed earlier, we usually do about 50 to 150 microns.
And then a follow-up on the talking about the gas is, instead of air, which gas is better to use? Nitrogen or perhaps something else?
So the testing has been done using both nitrogen, fuel gas, and it's shown that what you use does not affect the removal efficiency. So it just does not, it just should not have any of the contaminants in it. Otherwise, you can use any of the gases.
Yeah, in addition, if the bulk liquid, the raw liquid, did not have oxygen in it, the addition of air will introduce oxygen and therefore corrosion. So it's advisable to not use air because of corrosion issues.
Okay, a question on max feed TSS allowed. So what is the maximum feed for TSS?
Oscar, you want to take that one?
Yeah, sure. We can say that the maximum feed probably that we can take, it will be between, I will say about 200 TSS, I would think.
And then the what is the typical flow rate of the liquid that can be treated or to be treated?
You could do, and for different flow rates, we have different size of CoStrip. So we've done 100,000 barrel per day. We've sized one of those. So it would depend on the flow rate, and we can size accordingly.
Okay. Another question that came in is, what is the total holdup time for in the design? So the total design time.
Usually, it would again depend on the size, but we try to keep the gas to liquid contact about a minute. Oscar, am I right on that one?
Yeah, correct. Is about that. It depends on the application, obviously, but a starting point is about a minute.
Okay. Another question that came in is, to increase dissolved gas removal, would the vessel have more cells, or would the amount of gas per cell be increased?
This would again depend on the application, but the easiest way to do it would be to increase the stripping gas flow rate. This is to make sure that, and if you increase the vessel size, there will be more of a capex cost. So you can do it easier by just increasing the stripping gas flow rate.
Okay, I've got a two-part question here that came in. Can these units be placed in series to achieve the desired effluent concentration? And then the follow-up on that is, and does a system include a heat exchanger to increase influent temperature?
The system on its own does not include heat exchanger, but you could always add it. Now, you could add two in series to reduce the concentrations over and over. So you could do that technically, but I think it would be better to increase like a gas flow rate or the temperature to achieve a higher removal efficiency than adding more equipment into it.
Yeah, you can also increase the retention time on the vessel as well.
Okay, a question regarding ammonia. Can this be used for ammonia removal, and for instance, up to say 800 ppm?
I don't know this one. I'll let Oscar take it.
Yeah, for ammonia removal, I guess we looked at that application and on different times, and it's site specific, but what we can say is that every time that we look at ammonia removal that is over 100 ppm, it really goes exponentially on the cost. So that will be the answer on that.
Okay, another question is, what is the average retention time in CoStrip?
I think we answered that in a previous question. It's about a minute. The gas to liquid contact time is about a minute.
Yeah, that is a minute, I guess, per sail, so it would be a total of 4 minutes for the entire vessel.
Bear with me, I'm just reading through some of these questions here, making sure we don't get the same ones here. Let's see. Sorry, I've been jumping around a little bit, so I'm trying to make sure that we are not duplicating any of these here. Okay, another one is, what is the approximate size of the CoStrip unit? And then also, is it easily trailer mounted or able to move between sites?
If you're talking about the pilot unit, yeah, you can move it between sites. The size of it would depend again on the flow rate. So we have various sizes to accommodate that. If it's very big vessel, I'm not really sure if we can skid mount that, but if it's smaller, yeah, we have the capability of skid mounting these vessels.
Okay, I think we've got time for one more question. Let's see. Did you further optimize the process by having a step aeration, in parentheses here, microbubble, along with the treatment chambers? For example, 100% in chamber 1, then 75% in chamber 2, and 25% in chamber 4, and so on. And then the percentages are relating to the amount of air bubble that was introduced.
Technically, as you go through the vessel, we usually put in the same amount of gas through each of them. I don't know if you've actually tried different gas rates through each of the ductors. Oscar, do you know if we've tried that one?
No, we haven't done that. What we've seen is that on the first sails, you get the bulk of the removal, obviously, because you have the more gas. But then as it goes along, it keeps polishing. So if you diminish the gas, I guess you will not get the same performance.
Great. One last question here, and then we'll wrap up today's presentation. It's regarding the length of the vessel. The length of the vessel. The length of the vessel has any, does the length of the vessel have any direct impact with the CoStrip efficiency because of the temperature variation across the vessel?
You know, we don't think the length of the vessel has anything to do with the performance itself. The temperature inside the vessel is very constant.
Great. Well, thank you guys very much for your taking your time out of your busy days today. We do appreciate it. Thank you to Kim as well for taking the time to present the CoStrip technology to us. I do want to remind everybody, if you would please take the brief survey that is at the end of today's session as soon as we close out. That would be much appreciated. And you will also be entered to win a $25 gift card for that. And then furthermore, we are conducting a live webinar series, so we do have another week and a half. We do invite you to go to our website, www.veoliawatertech.com, to see the list of the upcoming webinar series, and we hope to see you at more of them in the future. Thank you guys very much.
All right.